Jai Hind, myself Richa from Department of Electronics and Communication, Ajay Kumar Garg Engineering College. Today we will discuss about the microwave measurement. This is the topic of the 4th unit also. Up to 4th unit we have discussed about what is the meaning of microwave, how microwave signals are generated, and first we will discuss from at which type of transmission technology we use microwave signal, in which we have discussed about the waveguide. After waveguides transmission line, we have discussed the microwave devices, various type of microwave devices. Because first we have generated this your transmission line, how the signal is behaving in the transmission media, then what are the different type of device we are using for microwave signals. After that we have discussed about microwave source, and in the last we will discuss the microwave measurement. It means we have generated a microwave signal and these signals are used in the microwave device, and how we can study this microwave signals. This is done in the microwave measurement. So microwave measurement is basically done from microwave test bench. Test bench is used to find out various characteristics of any generated microwave signal. So see here, first we have used a signal generator. This signal generator is microwave signal generator. From here we are using a microwave signal. So we can say this is your microwave source. So till now we have discussed about the microwave source also. So this microwave source is nothing, these are the microwave tubes, right? So microwave tubes, but in this microwave test bench we are using reflex klystron for generation of microwave signal. Okay, so here we are using reflex klystron. Klystron tube can be used for microwave generation of the microwave signal. Klystron tube is a very sensitive microwave source, so we have to use with the fan also, so there will be no heating effect. And after that there is a variable precision attenuator. Before that variable precision attenuator, there is one isolator is placed here, right? Isolator is a device which is used to give direction of microwave signal in a particular direction. It means it will allow signal to travel only one direction. So isolator is required so that signal will travel only in the forward direction. So signal will travel only in this direction, right? If there is some reflection from the load, so it will reflect it back to all the devices, but when it comes to the isolator, isolator will not allow this signal to go to the source. So basically the isolator is used to protect the signal generator. After that there is a variable precision attenuator we are using. So here we are providing the attenuation. There are different type of attenuators are available. So this variable attenuator we are using, it can be a pin diode type or plate type. If we are moving this pin or plate, the microwave signals are observed by the plate and pin, and if we are releasing it and we are giving path to the microwave signal, then signal will move towards the frequency meter. Next component used in the microwave test bench is the frequency meter. Basically this frequency meter is used to find out the microwave signal frequency. What is the signal frequency which is moving towards this frequency meter? So we can find out from this meter also what type of frequency is generated by the signal generator. After that, one slotted line section is used here. This slotted line section, from here we can connect a number of component. Here one crystal detector probe is used, and this is connected with some SWR meter, and Here crystal mount is here. We can connect CRO, any meter, power meter, VSWR, anything which we want to know or anything which we want to measure is connected through this slotted line section. So see, what is the signal generator? As the name implies, it generates a microwave signal in the order of a few milliwatt, and this use velocity modulation technique to transfer continuous wave beam into milliwatt power, because we are using the klystron tube here. So the velocity in the microwave tube, signals are generated through velocity modulation. Velocity modulation is nothing, it is the variation of velocity of electron depending upon the field through which it is interacting, right? So if it is interacting with a sinusoidal signal, and sinusoidal signal is present here and electron is coming out, and if electron will interact with the positive signal, then the speed of the electrons is increased, and if it is interacting with zero level of the signal, so speed of the electron will remain same, and if it interact with the lower negative side of the signal, then signal will be retarded like this. See here, this is one of the sinusoidal signal. Electrons are coming here. If electrons are interacting with the positive signal, the speed of the electron will increase, right? It will move with a high speed. If it is interacting with the zero level, speed remains same, and if it is interacting with the negative, then speed will decrease. High speed, it means it will take low time to reach. It means we are taking it as a reference electron. If speed is increased, then electron will take higher time as compared to reference. It means this is the time. Okay. Time taken by reference electron to reach at this point. This is the bunch of electron. Clear? So, accelerated electron will take lower time to reach to the bunch, and retarded electron will take higher time to reach to the electron. And this signal generator can be of gun diode, oscillator, or reflex klystron tube that can be used into the microwave signal generator. These two type of power supplies, or we can say these two types of microwave signals we are using with microwave test bench. Gun diode is based on the tunneling effect. From the tunneling effect, it will generate a signal, and gun diode and reflex klystron will generate a microwave signal. Second one component which is used is the isolator. After that, we have used the precision attenuator. This is the attenuator which select the desired frequency and confine the output around to 0 to 50 dB. This is a variable and can be adjusted according to the requirement. It means the desired frequency will be confined in between 0 to 50 dB only, right? Next component is the variable attenuator. This attenuator set the amount of attenuation. It means how much attenuation you want to provide into your system. Okay. So it can be understood as a fine adjustment of values where the readings are checked against the values of precision attenuator. Okay. So we can move the variable attenuator to provide attenuation. Isolator, this will remove the signal that is not required to reach the detector mount. Detector mount is a place where your signal generator is used. It means for the gun diode or reflex klystron, there is a mount, detector mount. Upon this, your source is placed. Isolator allows signal to pass through waveguide only in one direction. It will not allow signal to come backward direction. Next component is the frequency meter. This is a device which measures the frequency of a signal which is passing through the device. With this frequency meter, the signal can be adjusted to its resonance frequency. It also gives provision to couple the signal to waveguide. Basically, this is a measuring instrument which is used to measure the frequency, but it can also use to couple the two devices into waveguide. So we can connect in between a frequency meter and signal will travel through the frequency meter to other components of a waveguide test bench. Next is the crystal detector. A crystal detector probe and crystal detector mount are indicated in the above figure, where the detector is connected through a probe to the mount. This is used to demodulate the signal. See here. Right. So this probe is used to connect for demodulation. It means demodulation meaning this microwave signals we want to study. So how we can study? By seeing the waveform on the CRO, VSWR meter, or we can say the power meter reading. So this is called demodulation. Next is the standing wave indicator, or it is called VSWR meter also. So standing wave voltmeter provides the reading of standing wave ratio in dB. It will provide SWR readings. The waveguide is slotted by some gap to adjust the clock cycles of the signals. Signal transmitted by waveguide are forwarded through your BNC cable. This is connected with the BNC connectors. BNC cables to VSWR or CRO to measure its characteristics. So see here, this is a practical diagram, practical setup of microwave test bench in any lab. So see, this is your power supply basically. So this power supply, if we are using in the test bench, this can be a Cryston power supply, or it can be a, if we are using gun diode, so this will be your gun power supply, right? After that, this is the detector mount on which the tube is placed. This is your tube, reflect Cryston. One fan is using here. This fan is used to cool down the heating of Cryston, right? After that, one device which is used here, this is your isolator. This is a mandatory device after the source, right? After isolator, we are using it here, a attenuator. This is the attenuator. This is the probe. We are moving this probe, and if we are completely tight the probe, then complete signal is absorbed by this pin. Nothing will move out from this attenuator, and if we are releasing it, then we are providing some path to the microwave signal to pass to the another section of the test bench. So this circular type shape is the frequency meter. This is an analog circular cavity frequency meter. We can use digital frequency meter also. So this is the cavity. We can move this cavity to find out the resonant frequency of the microwave test bench. Further, we have using a slotted line section. This is complete a slotted line section. On this slotted line, we are using one detector. This is probe, and this probe is used to connect with different type of devices, right? And at the next end of the slotted line, here we have connected one device. This type of device is the directional coupler. Okay. So here we have connected one directional coupler, and we want to see the characteristics of this directional coupler at microwave frequency. So here the microwave signal is generated, and this microwave signal is passes through the isolator, attenuator, frequency meter, slotted section to the directional coupler. And if we want to find out the characteristic of a directional coupler, it means we want to know what is the VSWR directional coupler, what is the power output of directional coupler, coupling factor, isolation. So we will check all the parameters of this directional coupler. So this is your port 1, right, and port 1, 2, 3 and 1 is terminated. So from this port we will check the output. So this is, here we can connect any device, E plane, H plane, circulator, isolator, any device which we want to find out the characteristic of device. So from this microwave test bench we can find out different characteristic of a device. So if we want to find out the power of your signal, so what is the power measurement? So this can be done by the power measurement. The microwave power measurement is the average power at any position in waveguide. It means we can find out the power at any point of the waveguide. So power measurement can be of 3 types: measurement of low power, medium power and high power. Low power meaning the power between 0.01 milliwatt to 10 milliwatt. 0.01 milliwatt to 10 milliwatt. It means the signal less than 10 milliwatt can be measured using low power. Measurement of medium power, it means the power between 10 milliwatt to 1 watt. Signal up to 1 watt but greater than 10 milliwatt is measured through medium power, and the signal more than 10 watt will be measured from high power measurement. So low power measurement, it means power will be measured through bolometric technique. Medium power can be measured using calorimeter technique, and the high power is measured using calorimetric wattmeter. So measurement of low power, how this low power can be measured? Measurement of power around 0.01 watt to 10 milliwatt, 0.01 milliwatt to 10 milliwatt can be considered as measurement of low power. It means the signal between these power we are using the bolometric technique. In the bolometric technique, bolometer is basically a device that is used for low power microwave measurement. The element used in bolometer could be of positive or negative temperature coefficient, right? So if we are using the negative temperature coefficient, it means if resistance is, temperature is going to decrease, resistance is going to increase, right, in this way. So any type of temperature coefficient we can use it here, any of them can be used in the bolometer, but the change in resistance is proportional to the microwave power applied to the system. See here, this is one bridge here, and at the one arm of the bridge we are providing a microwave power, and we want to measure this power. What is the value of this power? Okay, so when we are providing power here, so the resistance of this arm is going to change because we are providing bolometer here. So if we are using negative resistance bolometer, so if we are providing the power to this, then the resistance is going to decrease like this. Okay, so the galvanometer is used to find out the deflection of bridge. If all the arms are, if galvanometer is at the 0 position, then bridge is balanced, and if there is unbalance because of the supplied power, then galvanometer will give some reading. So when this bridge arm is going to unbalance, so this complete system is going to balance this, and this balance is done by this circuit, and when this balance is given, then we are getting some reading at milliampere meter, right? So this bolometer is used in the bridge of arm as one, so that any imbalance cause affect the output. So milliammeter here gives the value of the current flowing, and battery is variable, which is varied to obtain balance when an imbalance is caused by the behavior of the bolometer. So this imbalance is in proportion to the voltage we are getting it here. So this adjustment which is made in DC battery voltage is proportional to the microwave power. The power handling of this circuit is limited. It means the voltage which we are getting it here, this is directly proportional to the microwave power applied here. So from here we can find out the power of your microwave signal. Next is the medium power. Medium power meaning the power between 10 milliwatt to 1 watt. This is the medium power. In this, a special load is employed, which usually maintain a certain value of specific heat, and the power to be measured is applied at this input, which is proportionally changes the output temperature of the load that is already maintained. It means we are using one particular temperature, specific heat, and if we are providing some microwave signal, then this temperature is going to change, and the difference in temperature rise specifically the input microwave power to load. So the change between the temperature of this load is directly proportional to the microwave power. So the bridge balance technique is used here to get the output, and the heat transfer method is used for measurement of power, which is a colorimetric technique. Okay, in this one type of fluid is used here, and we will use the initial temperature. After that, microwave signals is giving the temperature of this fluid is going to increase. The difference between both the temperature is used as a bridge balance technique, and the corresponding change in the resistance will be created here, and this imbalance will be solved by some external voltage applied, and this when this bridge will be balanced, and the corresponding external voltage is the output power of your microwave signal, and this is directly proportional to the input applied microwave signal. Reading is coming into the form of voltage, and there is one ampere meter is also connected. From this voltage and current we will find out the power, right? So voltage and current combination will give you the power. Next is the measurement of high power. High power means the power greater than 10 watt and up to 50 kilowatt can be considered as a high power. High power is normally measured by calorimetric watt meter, which can be of dry or flow type. The dry name is named as it uses a coaxial cable which is filled with dielectric of high hysteresis losses, whereas the flow type is named so as it uses water or oil or some liquid which is a good absorber of microwave signal. When microwave signal is given, then because of the heating effect of your oil, any liquid or water, it will be heat up, temperature of the fluid will increase. The change in the temperature of the liquid before and after entering the load is taken for the calibration of the value. So this change in the temperature is corresponding to the microwave signal applied, and the limitation of this method are like flow determination, calibration, and thermal inertia, etc. Right? Next measurement which we can do by the microwave test bench is the attenuation. In practice, microwave components and device often provide some attenuation. So that amount of attenuation offered by measured, it means any device which we are using in between, the device itself will provide some attenuation. Because of this attenuation, we are getting less power at the output. So how can we find out how much attenuation is provided by a particular device is done by the measurement of the attenuation. And measurement of this attenuation can be done by two methods. First is the power ratio method, and second one is the RF substitutional method. Right? So attenuation is basically the ratio of input power to the output power, and it's normally expressed in dB. So attenuation in dB is 10 log input power by output power, where P in is the input power and P out is the output power. So first method is the power ratio method. See here, this is setup 1, setup 2, right? So in this method, the measurement of attenuation take place in 2 steps. First step, the input and output power of whole microwave bench is done without a device whose attenuation has to be calculated. It means, see here, this is a normal microwave test bench, microwave source, attenuation, frequency meter, slotted line, and this is the termination. If we are not connected any device here, so we have to terminate it with the matching load. And here crystal detector, through this crystal detector we are using one thermistor mount and power meter, right? So first we will measure the power of the microwave test bench without any device. In the next step, the input and output power of the whole test bench is done with the device whose attenuation has to be calculated. See here, now we want to find out the attenuation of this device. It can be magic tee, directional coupler, it can be a isolator, circulator, any device. So now we will attach the device in between this frequency meter and slotted section. We are providing a device whose attenuation we want to measure. So this device we are using it here, and after that the same system we are using and we find out the power, right? So the difference between these two power is the attenuation of this device, or we can say the ratio of these two power, basically the ratio, because P in by P out, okay. So the ratio of these two power is the attenuation of the particular device. But there is some drawback. Drawback is the power and the attenuation measurement may not be accurate when the input power is low and attenuation of network is very high. If input is very low but attenuation is very high, so this method is not accurate method. Next method is the RF substitution method. So again, microwave test bench setup is here. It is done in the 3 steps. First step, output power of microwave test bench is measured with the network whose attenuation has to be calculated. So see here, this is the network or device whose attenuation we want to measure. So we will calculate the power by using this P1. The output power of the microwave test bench is measured by replacing the network with the precision calibrated attenuator. Now in place of this, we are using one variable precision attenuator, right? And variable precision attenuator, now the attenuator is adjusted to obtain the same power as measured with the network. It means if this power comes out to be 30 dB, so now we will replace this device, and in place of this device we are using a variable precision attenuator, and from this variable precision attenuator we again want a reading of 30 dB. For this 30 dB, precision has to be done, or we can say the attenuator has to be varied. So how much attenuator is varied is the attenuation of your device. If it is attenuated by 5 dB, 4 dB, so this will be the attenuation of the device. Next measurement is the frequency measurement. It means we want to measure the frequency of the signal which is moving in the microwave test bench. So microwave frequency can be measured mainly by 2 methods. One is the slotted line method, this is called indirect method. Second is the resonant cavity method, which is called direct method. So slotted line, the standing wave setup in a transmission line or a waveguide that produce a minima for every half wavelength apart. So see signal generator, variable attenuator, frequency meter, then slotted line, crystal detector, and from this crystal detector mount we are connecting a one VSWR meter, and this is your mass termination. So here we are getting some readings, waveform. So this is the method of how to calculate VSWR using slot. So if it is a analog meter or digital meter, you can get direct reading into the dB. So these minima are reflected. Basically this minima, if you want to say, we can see it from CR only, right? In this meter only, meter, from here we can get the direct reading of your VSWR, right? So these minima are detected and the distance between them is measured. It means we will find out the distance between two minima, okay, or two maxima, anything you want to find out. So the wavelength and the frequency can be calculated. So wavelength is twice of d minima, right? And frequency is c by lambda naught. What is lambda naught? Lambda naught is equal to lambda g lambda c divided by square root of lambda g square plus lambda c square, where lambda naught is the free space wavelength, lambda c is the cutoff wavelength, and lambda g is the guide wavelength. And d minima can be measured by the slotted line probe carrier. So how this d minima can be calculated? See here. So these are two minima, first minima, second minima. These are two maxima here, right? So distance between two minima is d minimum, right? Next method is the resonant cavity method. So the most commonly used type of microwave frequency meter is the wave meter. It means we can directly find out the frequency from the wave meter. From this wave meter, we can calculate the frequency. It consists of a cylindrical or coaxial resonant cavity. The size of cavity can be altered by adjusting this plunger. Basically, there is a one plunger here. From this plunger, we can vary this, and the size of the cavity can be changed. And the cavity is designed in such a way that for a given position of the plunger, the cavity is resonant only at one frequency, that is specific. It means at a particular position it will be resonant at a particular frequency. So according to this position, we can find out what is the resonant frequency of the cavity resonator. Next is the measurement of Q of the cavity resonator. There are several methods for measuring the Q of the cavity resonator: transmission method, impedance method, transient decay or decrement method. Among these, transmission method is the simplest one. So transmission method for measurement of Q of a cavity resonator. The setup for transmission method of measuring, see here, this is microwave source, attenuator, here we are using a cavity resonator, okay. After that we are using detector and power indicator. So in this method, cavity resonator act as a device that transmit, and the output signal is plotted as a function of frequency, which result in a resonant curve as shown this. It means the output power with respect to frequency is plotted. So it comes out like this: 0 dB, minus 3 dB, and that the minus 3 dB, this is twice of D. So from the setup, the signal frequency of the microwave source is varied, keeping the signal level constant, and then the output power is measured. The cavity resonator is tuned to this frequency and the signal level, and the output power is again noted down to notice the difference. So from the resonance curve, half power beamwidth, which is at the 3 dB minus 3 dB, to delta is equal to plus minus 1 upon QL. What is that QL? QL is the loaded value. So QL is equal to, if I am rearranging this equation, plus minus 1 upon 2 delta, which is equal to plus minus omega 2 omega minus omega naught. So if the coupling between microwave source and the cavity and that between detector and cavity are neglected. If we are neglecting this type of coupling, then QL is equal to Q node. It means unloaded Q. However, the accuracy of this method is poor, particularly in case of very high Q system due to narrow band of operation. Next is the measurement of VSWR. In any microwave practical application, any kind of impedance mismatches lead to the formation of standing waves. So, the strength of these standing wave is measured by voltage standing wave ratio. So, the ratio of maxima to minimum voltage gives the VSWR. It can be, we can find out V max upon V minimum. And in terms of reflection coefficient, it can written 1 plus rho, 1 minus rho. Rho is nothing, that is the reflection coefficient. It means what is the reflected power upon incident power. What is the ratio of this? So, measurement of VSWR can be done in two ways. One is the low VSWR measurement and high VSWR measurement. Low meaning the value of S or SWR is less than 10. So, measurement of low VSWR can be done by adjusting the attenuator to get a reading on a DC millivoltmeter, which is VSWR meter. It means we will vary the attenuator to find out a reading at VSWR meter. The reading can be taken by adjusting the slotted line and the attenuator in such a way that the DC millivoltmeter shows a full scale reading, right, as well as a minimum reading. It means it will be able to go between minimum and the maximum value. Now, these two readings are calculated to find out the VSWR of the network. Measurement of high VSWR, it means more than value of VSWR is greater than 10. The measurement of high VSWR whose value is greater than 10 can be measured by a method called the double minima method. In this method, the reading of minimum value is taken and the reading of half point of minimum value, the kissed before and the kissed after also take. It means if this is the minimum point, we will take one reading in this direction, another reading in this direction, and this is nothing, this is, we can say 3 dB down, right. So, we are taking two reading here. So, this is your D1 and D2, this is V minimum, and the VSWR from these two reading can be calculated lambda g upon pi D2 minus D1, the difference between these two distances. So, lambda d is the guided wavelength, lambda g is equal to lambda naught upon 1 minus lambda naught by lambda c square. Lambda naught is nothing, that is your free space wavelength, it is calculated from C by F. As the two minimum points are being considered here, this is called double minima method. Thank you very much. This is all about the measurement of your microwave signals and what are the different characteristics we can use from microwave test bench.